these two. And they're really just a matter of memorizing them. So delta x divided by 2, and then it's the value of the function at x0, 2 of them at x1, 2 of them at x2, 2 of them at x3, and 1 of them at x4. So you follow your instructions, right? They tell you that's what you do. That T4, right, it's a 4-strip approximation, and it is more accurate than left or right. But you have to do a bit more work because of that. Now, the ultimate accurate, right, for any given number of strips, the numerical estimate technique that's going to give you the most accurate result for any number of strips is called Simpson's, and it's Simpson's 4. And its formula is uglier than all the others. It's delta x divided by 3, the value of the function at x0, 4 of the next guy, 2 of the next guy, 4 of the next guy, and you finish with 1 of the last. And you don't need to know why on earth it is that. Can you just trust me? I'm a mathematician, and it is that, right? So what I want to do today, because these are so darn long, is I'm going to show you 2 examples of us doing some of these questions, just to show you the process. And I'm probably going to skip some corners, but that's fine, I'm allowed to. So here's my first one. Suppose you had this function between 1 and 2. It's not unlike one of the 4 homework questions from 7-7, right? There's only 4 of them, but there are a lot of work in each 4 of those questions. And we're going to find L4, R4, midpoint 4, trapezium 4, and finally Simpson's 4, right? So what's the first thing that we should do in this situation is that we should find delta x. And that never changes. Delta x is the start and the finish divided by n. In this case, 2 take away 1 divided by 4. So it's nothing 0.25. So that would be my step 1. Step 2 in every single one of these questions is create a table with the values that you're going to use. So I'm going to have an x and the value of the function. And I'm going to start at 1. And I'm going to go up in 1.25s. And I should finish at 2, which I do. And for each one of these guys, I'm going to find the value of the function. And I'm going to do the shortcut, which is basically I'm going to set up my table. Oops, almost forgot. Isn't the first thing you need to do is to type in what the function is. So in this case, it's the square root of 2x adds 1. Then I'll go table setup, and I'll start at 1, which is good. And I'll go up in 0.25s. And that's it. I can now get all the answers I want. This first one, I guess I'll put it to the side here. Now I'm going to cheat here. You really should be doing these answers to 4 decimal places, right? Because that's what they want in most of the homework questions. I'm going to cheat just for speed and just do things to 2 decimal places, right? But can you imagine that you would have to do it to a little bit more accuracy? So this guy is 1.73. This guy is 1.87. This guy is 2. This guy is 2.12. And the last one is 2.34. So step 2 is get your table to whatever accuracy you need to work to according to the homework question. And some of the answers are going to be 6 decimal places. That might mean that you can't do the shortcut. It might mean you have to do 6 separate calculations, and you'll have to make your table bigger so you have enough space to put these in. Or you could make your table vertical, and that would work too. Now, when I do the table, I typically, because I'm careless, name the x values according to their x0, x1, x2, x3, x4 value, right? And now I'm going to do one of these guys. I'm not going to do all of them because it would take forever in the day, but I'll do one of these. An L or an R, which one do you want? I'm letting you pick.
R.
R it is. Now, if I do an R4, isn't that going to be the right-hand 4, right? These guys. And so my formula, whoops, my formula is going to be delta x times that guy, that guy, that guy, and that guy. Delta x, clear, second, quit. Delta x is 0.25, so here we go. 0.25 times, in brackets, 1.87, add a 2, add a 2.12, add a 2.34, and hopefully you get the answer 2.0825. And that table got me that fella. Now I want to get T4. Now T4 is delta x over 2. And if you look at its formula, it's the first guy, twice the second, twice the third, twice the next one, and one of the last. So it's going to be one of these, two of them, two of them, two of them, and one of those. See how that works? One of these, double that, double that, double that, and one of these. So let's see what that looks like. It's going to be 1.73, two lots of that guy, two lots of that guy, two lots of that guy, and finish with just one of those guys. Are we comfortable with where the numbers are coming from? Basically just following the instructions, right? Just using this formula.
Sorry.
Now yes.
If there were more than, like if it continued past x4, would you multiply the two still by everything except the first and the last value?
Correct.
Okay.
Yeah. So see if you did an L10. God, please don't have an L10 question. That would drive me crazy. But if you had an L10 to do, wouldn't you use one of the first ones, double, 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 and only one of the last one? Right? And so you just continue that part. I've shown you what it's like for 4, but can you imagine for 6 or 8 or 22, it would be the same pattern. One of the first, one of the last, and double everybody else in the middle. We cool? Right, let's go. This is scary time for me. 0.25 divided by 2 times, in brackets, the first guy plus 2 times the second guy plus 2 times the third guy plus 2 times the next one plus one of the last guys. Close the brackets, enter, and I get 2.00625. Okay. Now, in the big scheme of things, left and right are not very accurate, right? They're easy to do, but they're not great. Trapezium in general is better than either of those. So in general, I could say that this estimate is probably closer to the true answer than that one. But in both cases, doesn't it look like the answer's probably pretty close to 2? Somewhere in 2, 2.1 would be my gut feeling, right? So we do have a good ballpark figure, right? We know it's 2 and a bit, 2 or 2 and a bit. So far, so good. It's not hard to do. Do you see? It's just, oh, what's the word? Boring, right? It's just tedious, right? You just follow the instructions and you've got it. So for the last one of this one, I'm going to do an S4. And that is delta x over 3. And the pattern this time is 1 of the first guy, so 1 of him, 4 of him, 2 of him, 4 of him, and 1 of him. So that's going to be 1 of these guys, 4 of this guy, 2 of this guy, 4 of this guy, and finish with 1 of the last guy. Can you kind of follow the instructions of why I'm doing what I'm doing to each of these values? Now, if that last one was bad, this one is going to be even worse. So here goes 0.25 divided by 3 times, in brackets, that first one, 4 times the next guy, 2 times the next guy, 4 times the next guy, plus the last guy. And the answer that we get here is 2.0025. Now, in the big hierarchy of things, for the same number of strips, an S4 will be the most accurate estimate. T4 is next, and left and right are at the end. Sometimes left's better than right, because isn't sometimes one of them is an underestimate and the other's an overestimate, you know, that kind of thing. But if you had only one to do, always pick S1. So what's the drawback? It's uglier. Don't you have to keep track of more things? And you have to do more calculations. Now, side note, if you are interested, where on earth did these formulas come from? Let me show you how they came about. Imagine you've got your function, and you start here and you've got whatever it is, so many strips. You take each strip, and for the trapezium, you don't use this guy, you don't use this guy. What you do is you join them together, and you don't make a rectangle, you make a funny little shape that's called a trapezium. Hence the name trapezium 4, right? T4. Now you can find the area of that, because basically isn't it a rectangle with a little baby triangle stuck on top? If you found the area for all of those guys, this is what the formula ends up looking like. Now, if you think about it, can you see that a straight line might not be perfect? But isn't it better than a rectangle? So a trapezium shape is a better estimate than using rectangles. That's essentially what that says. Now, what's next? Simpson's rule. Ugh. Well, I'm not even going to try and draw this accurately. What Simpson's rule is it takes a strip, right? Like say that was the first strip, right? Like that. And it makes a quadratic curve that goes through the 2 points. So it basically joins it with a curve. And this is what the formula is. Quite weird how it happens, but this is what the formula looks like. And can you imagine that shape, because most curves are curved, right? Wouldn't it be even better fit than a straight line joining the start to the finish? And that's why it's so accurate. So if you are interested in where it came from, there it is. But for practical purposes, don't you just have to use the darn thing? So here are some of those guys, right? There's 3 out of the possible 5. Do you feel comfortable that if I give you a function, you can create the table, and then from this table, depending on what you're going to ask to find, an R4 or a T4, that you should be able to do it? Does that seem reasonable? Boring as hell, but doable. Right.
I just had a quick question, if that's okay. Sure. So like on the exam, you'll just ask like find the L4 or R4 for this specific function.
You'll get a homework question type, So you probably won't get any questions in the test.
Okay.
And that's just because these things take so bloody long.
Oh, okay.
And I'm assuming that since you've done the homework, you've at least done them once. So that's the cop-out for me. I don't ask you any questions to do them, right?
Oh, okay, that makes sense. All right, thank you.
Okay.
Good, because I'm super slow.
Yeah, that would. Yeah, but if you're being
too.
careful, yeah, if you did this, if you were being careful, the test would be over before you'd finish the first question. So, no, we will. The questions in the test are going to be from sections we haven't done yet. The algebra stuff, right? The cool stuff, as I call it. Okay, so that was my first example. I'm only going to show you 2 of these. You can understand why, right? Take forever in the day. So here is a different function. Its start and finish value are awkward, so I picked it because of that. And one of the homework questions looks quite like this. And you're going to be asked to find a whole multitude of lefts, rights, and midpoints, and so on. So I'll start with my usual step 1, which is find delta x. In this case, a is 0 and b is pi. So far, so good. Now, in this particular table, we're going to have your x's. And obviously after that, the f of x part, which is what step 2 is about. And we're going to start at 0. And I'm not going to turn that into a decimal. Okay, if you're wondering why some of these fractions look funny, 1/6, 2/6 simplifies down to a third, 3/6 simplifies to a half, 4/6 becomes 2/3, 5/6 is 5/6, and isn't 6/6 1, right? So I did start at 0 and add delta x all the way up. Are we comfortable with that? These guys here, I could do as a table of values on my calculator, but, well, not a but, it's just downright, what's the word I'm looking for? It's downright messy. Secondly, some of the questions want 6 decimal places, not 4. If I do the table of values, I only get 4 decimal places. Can you see that when I put my answer down, my answer won't be quite the same as if you did your stuff to 6 decimal places? So you're now about to see the worst case scenario where you have to do every single one of these by hand, using a calculator, of course. So I guess it's not totally by hand. Right, so I'm making sure that I'm in radians, which I am, which is an easy mistake to forget. And the first one's going to be the sine of 0 squared, which is the sine of 0, which is 0. And the next one's going to be the sine of pi upon 3 squared. So I'm going to go bracket pi divided by 3, close brackets, squared, do a bracket. You need that extra set of brackets just to keep the calculator happy. If you miss some of those brackets out, you might end up with pi over 9 because it thinks the 3 is being squared and not the whole fraction. Now, when I hit that, you can see I get a really, really accurate answer. And if they wanted it to 6 decimal places, can you imagine? Okay, you only do it once. So that's the only saving grace, right? But you do it anyway. I'm going to cheat and just do it to 2. Now, if you have to do a whole load of questions over and over again, and you can't use the table of values because they're not accurate enough, it would be nice if there was a kind of shortcut where you could at least reduce your workload a little bit. Agreed? So here's a shortcut. Down at the bottom of your calculator here, it says in blue entry. If you hit second entry, it brings up the calculation that you've just done. You can then scroll over to the 3 and change it to a 2.
Sorry, a quick question, Professor Robertson. Do you mean
Yes.
to put that under pi minus or pi divided by 3 or pi divided by 6?
That's a
Yeah,
mistake. My apologies. I covered up one. Right, so I'm now about to do out of sequence pi upon 6, the one I should have done first. Right, but isn't it cool that you can actually just recall the thing and change one number, so I don't need to type too much. So the first one is in fact 0.27. That one I've done. Second entry, the next one's going to have a 2 there. And that's going to get me 0.62. Next one's 2/3. That's going to be a little bit messier. So I could, I guess, insert a 2. Make that a 3. There we go. And that's going to be, oh, didn't expect that, negative 0.95. Almost done. The next one is going to be 5/6. And the answer here is 0.54. I know that one's 0. Okay. Can you imagine that you're more careful than I am and you get the whole table done to 6 decimal places? Right. Now, I could do a left and then a trapezium and then a Simpsons, but for the life of me, I think once you've done one of these questions, haven't you done all of them? Right, so I'm just going to randomly pick one, not the midpoint one because we haven't got a table set up for that. But would you want trapezium or Simpson? Because they're the 2 new guys that we haven't done now. You want a T6 or an S6?
S6.
Let's go for it. S6. Well, according to the formula, it's delta x over 3. And now we have to adapt it. This is what it looks like with 4. And the pattern is one of these, 4, 2, 4, and one of these. So it's going to be one of these guys, 4 of these guys, 2 of these guys, 4 of these guys, 2 of these guys, 4 of these guys, and 1 of these guys. Do you notice that the pattern is continued? Instead of, like for the trapezium, isn't the pattern 1, a whole load of 2s, and finish with a 1? But for the Simpson, isn't the pattern a little bit messier? It's 1, 4, 2, 4, 2, 4, 2, 4, finish with a 1. We go with that? Right, plug the numbers in. 1 of these guys, 4 of these guys, 2 of these guys, 4 of these guys, 2 of these guys, 4 of the next guy, and 1 of the last guy. Okay, here goes. Delta x. Ooh, pi upon 6. That's going to be fun. Brackets. Pi divided by 6. That's pi upon 6 divided by 3. Times A bracket. That guy is 1 times nothing, so I'll just put in nothing. Add 4 times the next guy. Add 2 times the next guy. Add 4 times the next guy. Add 2 times the next guy, which is negative. Add 4 times that guy, and finish with 0, which I won't bother with because it's 0. And I am looking at 0.977 and all of the other stuff. So wouldn't it be nice if we could check in some way that this wasn't wildly wrong, right? Looking at this answer, if you were a betting person, would 1 be a reasonable guess at what you think the perfect answer might be? Darn close to 1, isn't it? Oh, let's just find out. Show you how you can do it. Oh, I know what I can do, because that's a tiny little one. I am going to show you on my emulator, which is a bit bigger, and that might be a bit easier for you to see what I'm doing. So if I'd thought about it, I probably should have done that away all those calculations, but too late now. Right, you see my nice big calculator? Right, I'm going into any mode. I am in radians, that's good. I'm going to go here and show you, and this is one way to do it, there's others. And I'm going to type in the sine of x squared. And I'm going to go to my window, and it starts at 0, and it finished at pi. And then I'm going to do zoom 0, which is just so I can make sure it's right. And that's what it looks like. And now I'm going to find out what the answer. Oh, do you know that one of our answers was negative? Can you see how come it ends up being negative? Because it's probably one of these guys here. So that wasn't surprising that I see it. Now I'm going to do second calc. And you see the guy called number 7? That fella. And it's going to say lower limit, which is 0. Hit enter. It's asking for the upper limit. So you hit pi. Oops. My eyesight. There we go. And I'll hit enter. And it'll do its little thing. Oh, darn it. 0.7726. I'm worried. Now, it could just be that S6 just isn't a very accurate estimate right now. And it could be that I screwed up.
Yeah, when x is pi, I think it's negative like 0.43.
Yeah, you only evaluated it up from 0 to pi, though. Like past pi, there's more.
Pi squared is not, that's it. That's where I screwed up. See that last number? It should have been the sine of pi squared. And I just assumed, because I wasn't being careful, that I knew the answer to that. The sine of pi is 0, which is my mistake. But it's not the sine of pi, it's the sine of pi squared, which is that negative 0.43. Now I can fix that. In fact, isn't that a good call? That was worrying to me. If you change the last guy to being this guy and you recalculate it, I bet you I'll get an answer much closer to that one. So 0.977 subtract 0.43 times pi divided by 6 divided by 3 and 0.977 take away 0.2506, and the answer that I get the second time round, and that is much more comforting, isn't it? I think one of the reasons I dislike these kind of questions is I am noticeably careless. And did you see how easy it was just to skip one little assumption and your answer's out? But hopefully I fixed it. Right, so I guess the question now is, if I gave you a function, would you be happy about finding delta and creating a table? And then depending on what you're being asked, use the formula, do all the boring number crunching stuff and get an estimate. And we're already 30 minutes through this lesson, and when technically I've only done 2 questions. But there are 4 in 7.7, so have fun. So what's left? Well, let me show you what the questions are that we haven't done from the earlier section. That means I need to leave this one. You hold on for a few seconds. Here we go. There. There's a whole bunch of questions towards the end, which I'm scrolling by relatively quickly for the time being, so we can get to here. Remember we did the sigma? Hopefully we did the sigma. You remember we did that? Right. So we've kind of covered 11, 12, and 13. And then the last few questions involve this stuff. And that's kind of where I'm going to work on now. I should give you like a health warning. You are not going to like the next 20 minutes. What we're going to look at is the theoretical version of how do you find the exact value of an area under a curve. And that is going to involve us doing quite generalized algebra, for want of a better word. So let's imagine that we had such a problem. And we had some function, y equals f of x. And it started at A and it finished at B. And we decided to split it into n strips. So do you see here, everything is general. I'm not telling you who f of x is. I'm not telling you what number A or B is. I'm not even telling you what number n is. What we're going to do is construct what the process would be to find Rn, right? The right-hand side with n strips. Now, my little fella over here tells me how you would find Rn. It would be delta x, f of x1 plus f of x2 plus all the way to f of xn. And now what I'm going to do is I'm going to figure out what the heck these guys are. And in particular, I'm going to take this and I'm going to do it using sigma notation. Now, if you multiply all these things out, that is just another version of what Rn would look like in general. Which means that I could write that down as, what letter of the alphabet shall I do? K equals 1 to n of delta x, f of x subscript k. Are you happy about this can be written with that sigma notation? K equals 1, K equals 2, K equals 3, finishing, K equals N. So let me put this guy over here, and let's figure out who delta X is. Isn't delta X B minus A over N? Agreed? Now, let's figure out who X1, X2, X3, and in particular who XK would be. Now, can you imagine that I just draw the X-axis? And that's A, and right at the end we've got B. Isn't A called X0? Now, won't the next guy, then the next guy, and the next guy, and the next guy? Well, let's see what they would be. This guy's called X1. The next one's called X2. Next one's called X3, right? And so on. What would the value of this fella be? Well, how about A add a delta X? Would that be correct? Now, what would X2 be? Well, wouldn't it be A add 2 delta X's? And X3, wouldn't that be an A add 3 delta X's? So far, so good. Now, imagine this was a random guy called XK. What would XK be written as? Two gets you that, 3 gets you that. What would K get you?
X plus K delta X.
Right? A plus K delta X. Which means that this guy over here can now be written as sigma K equals 1 to N delta X F of A plus delta X, where delta X is that guy. So far, so good. Right. Now, if I wanted to get a perfect answer to the area under a curve, wouldn't I make the number of strips go infinite? Does that make sense? If you could theoretically take an infinite number of strips, wouldn't you end up with the perfect area? And in our case, that becomes the limit as n tends to infinity of all of this. I'm about to move on. This might be one of those times where you'll go back to the video and pause it and say, where did that come from? How did you get this line? And so on.
Hey, can you explain really fast? The handwriting is a little bit rough on the right side there on the bottom. Yes, yes, sir.
Here, that says delta X, F of A plus delta X. So I'll write that again. This is what it looks like. It's the limit as n tends to infinity of sigma K equals 1 to N of delta X F of A plus delta X, close brackets. Yeah, it's a cleaner, hopefully a cleaner version of what that is. Yeah, you can imagine then that that is very theoretical, right? There's not even a number in sight, I guess one is there, but that's it. And you might say, well, how can that help us to get the exact area under a curve? Well, we don't do very many of them. In fact, I think we do one where we actually do it from start to finish. And I'm going to pick that one tomorrow. But we can answer some of the other questions that use this. So I'm now going to go and look at some of these homework questions, which are based on what we've just been doing. Okay. If you look at the top of question 14, right, this guy up here, he is essentially, they're called Riemann sums if you want a name for that thing. These are Riemann sums. In this here, you should be able to tell who the function is and what A and B is. So here goes. See this tan guy? Does it not tell me that the function is tan x? So it's maybe that answer, or it might be that answer, or it might be that answer. Okay. Now, what is this guy, the pi over 6n? Pi over 6n. Isn't he my delta x? Right? That's where the delta x would be. So when I look at this question, I'm saying, okay, where do you start and where do you finish? Well, I'm looking at this thing here. Do you see any pi plus this or pi upon 2 plus this? I don't see any start. That tells me that you start with a 0, which means that the answer is either this one or that one, right? Tan x starting with a 0. Now, if this thing up here had said pi upon 2 plus this fraction, then I would have said, oh, a would have been pi upon 2, because in our formula, isn't it a plus delta x with an I in it, right? So last bit, does it finish with a 6 pi or does it finish with a pi over 6? The last number here is n. If you make this fella I and n, the n's cancel and you're left with pi upon 6. So that makes it that one. So we've just done question 14 homework. It ends up being the bottom one. We've got seconds left. This is basically question 15. This is what the function looks like. There's the delta x calculation. There is the xi calculation. Here is all the pieces being, altered. There's the delta x. There's the a plus delta xi, and there's the a plus delta xi here. So I'm just going to leave that for a second, and you can pause it in your video when you want to go and look at it. But that's the solution to question 15. That's